Okay, in this video, let's take a look at one of the most common physical phenomena that we experience every day and we actually rely upon to be able to live in the world in the way in which we do on a day-to-day basis, and that is gravity. Gravity in terms of how it affects things in free fall. Now, when we talk about free fall, really we're talking about forces. So I don't want to get too detailed because forces will be the next unit when we talk about the why behind gravity. But in our everyday experience, we know that gravity affects objects in a specific way. And we can start with just a very simple example. Let's take dropping a ball, right? If I hold a ball above some surface, like the ground, I lift it up, it's not moving, it has a velocity of 0, it's an initial velocity of 0. And then when I release it, we know that it accelerates. The reason we know that is it always is going to move down towards the ground. So the ball will accelerate downwards. And the reason it accelerates downwards is we say it's gravity, right? Well, it's gravity. Okay, well, what is that? Well, gravity is due to the presence of the large mass of the Earth. And so as long as we're near that Earth, the presence of that mass with an object of mass will cause that attraction and cause that object to accelerate. So very easy to see that velocity increases in the downward direction because of gravity when something falls. And we say it's in free fall when really gravity is the only thing affecting it. So we're neglecting the effect of the air, which we'll get into more detail later. But for now, free fall implies balls falling, something's in the air, only gravity is affecting it. Now, what about if I throw a ball with some initial velocity that's positive? So positive meaning in the upward direction. Does gravity have an effect on it in the same way? Well, we can answer that question by looking at the trajectory of the ball. So let's not look at 2 dimensions yet. Let's just look up a single dimension. The ball travels up. It's going to reach some maximum height unless we can throw the ball at a crazy initial velocity to allow it to escape the gravity field of the Earth, which I'm not sure anybody here is able to do. Maybe you can die trying if you'd like to, but I think it would be a futile effort. You're going to throw the ball up, and at some point that ball is going to fall back down towards the Earth. Now, what's happening to the ball throughout its flight? Well, as it's going up, it reaches a peak where we can say it momentarily stops, right? It has to change direction. When it changes direction, its velocity is what? Well, if I'm going to the right and I stop and I go back to the left, at that instant that I change direction, my velocity is 0. And we can show that on the graphs here when we get down to those in a second. So the ball goes up, it slows down, right? On its way up, it has to slow down because it was given some initial positive velocity and it ends up stopping and coming back down. So it slows down. So if I have something with a positive velocity, in what direction must the acceleration be in order to slow it down? Well, if it has positive, to lose that positive velocity, I must have a downward acceleration on the way up, right? So I reach the peak of my height and then I fall back down to the Earth. Well, now I gain negative velocity. So the velocity increases in the negative direction. So again, the acceleration, I should be using the same color here to not confuse you guys. The acceleration is still downward. So throughout an entire flight of an object in free fall, whether it's dropped or whether it's thrown upward, the acceleration is always negative. And that value, if close to the Earth, is 9.8 meters per second squared downward. And sometimes we're going to call that negative 9.8 meters per second squared when we're doing problems, because when solving a problem, it's very important to denote our reference frame and our if this is our standard coordinate systems, usually up is positive, down is negative, to the right is positive, to the left is negative. So we're going to treat the downward acceleration of objects due to gravity as negative. All right, one more thing I want to show you before we solve some problems is what these look like graphically. If I were to graph the falling position of a ball, let's say I lift it to some initial height off the ground, and then let's call my ground my 0 point, my 0 position. Well, what's going to happen? Well, it's going to start initially at rest, so it has to have an initial flat slope, because remember the slope of this is the velocity, so it has to have an initial flat slope, and as it falls, it accelerates due to gravity, so it's going to be increasing in the downward direction. So over time, my position time graph would look like this, where I have the velocity increasing in the downward direction. All right, well, what would my velocity time graph look like? Let me try to change up colors. I should be doing this all along. I'm going to confuse you guys. Remember, my initial velocity is 0, so I start at 0, and then it decreases, because remember, negative is down, so it decreases in the downward direction over time. So it's going to be a downward sloping line. And then finally, my acceleration graph. This acceleration, so long as I'm close to the Earth and it's the only thing acting on it is gravity alone, it's a constant rate. The rate of the acceleration does not change. So that acceleration is constant, and it's negative because 9.8 is the acceleration downwards towards the Earth. We call down negative. So this value would be a flat line at 9.8 meters per second squared. Now if I throw the ball up in the air, so let's say I started at a position of 0. Okay, so I'm giving it some positive velocity, so it's going to have some initial positive slope. As it reaches the top, it's got to flatten out because its velocity decreases and then it changes from positive to negative. So if I go from positive to negative, I have to cross 0. So it goes from positive to negative, and then it decreases downward. So I've got the full arc here. So this is where I'm at the top of my flight, where the velocity is 0. What's the acceleration at this point? Okay, just because the velocity reaches a point of 0, the acceleration does not change. The acceleration is a constant negative 9.8 meters per second squared throughout the flight of the path. So on the way up, the acceleration is still downward. On the top, it's still downward. If it wasn't, if the acceleration was 0 here, then it wouldn't continuously fall. It would stop and it would stay there, and it doesn't happen. It continuously follows its trend of going up and coming back down. All right, velocity. Now I start with some initial positive velocity above 0, but as soon as I leave, it starts to decrease. The slope gets shallower, so it decreases. When it crosses 0 is when I'm at my peak or at the top, and then it continues to decrease in the negative direction. Well, remember, the slope of this is my acceleration. The slope of this is my acceleration. These two lines, notice they have the same slope, and that slope would be negative 9.8. The acceleration due to gravity. So whether I throw the ball up in the air or whether I drop it, the whole time it's free fall. It's considered free fall. Gravity is the only thing affecting it, and the downward acceleration is a constant negative 9.8 meters per second squared throughout its entire flight. At the top of the peak, the velocity is 0, but the acceleration is still always negative 9.8 throughout the entire path of the ball.